All right. Welcome again, everybody. I'm Arthur O'Dwyer, and this talk is on Lambdas from first principles. This is designed to teach you all about Lambdas and what they are and how to use them, and that they are not, in fact, big, scary, Lispy, functional programmy things. They actually interoperate really well with C++, and here's how you use them. I like to be a little bit interactive, but also not super interactive with questions, because we do have 68 slides, I think, to get through in an hour. But basically, for questions, if I'm going along and you have a question about something, and it's a question about, like, I don't get what you just said, or doesn't that contradict what you just said, please do raise your hand, and I'll try to clarify. If you have a question like, okay, I see how that works in that case, but what about the case where it's a Variadic template? Please don't ask those questions until the end, because we probably will get to that in about 5 slides. So no questions that complexify things. Yes questions if you're confused about the concept, because the point of this is really to explain the concepts. Okay, so Whirlwind tour of C++. Let's start really simple. Plain old functions. Because lambdas are kind of like functions, right? So yes?
Sorry, I didn't. You're good.
All right. Plain old functions. Here's a function. I named it +1. What it does is it takes its argument and adds 1 to it. Over on the right, I'm showing the disassembly. I'm going to be showing some disassembly as we go along. This is what you would get if you compile it with Clang on, I believe this is a OS X, just because that's my platform of choice. So x86, 64 with the Clang mangling scheme. How many people are familiar-ish with, like, name mangling in C++? Bunches. Okay, good. So you all know what that means. Okay, so that's easy, right? It's a function. It's a named chunk of code. The name is some mangled form of the function. C++ lets us overload functions. I can have a function named +1 that takes an int. I can have another function also named +1 that takes a double. And then if I call +1 with an int, I get one version. If I call +1 with a double, I get a different version. And this is indicated at the assembly level by a difference in the name mangling of the function name. So 2 blocks of code, both callable as +1 in your C++ code, but of course they have different name manglings. So far, so simple. We all know this. Function templates. So C++ also lets us write templates. So when we want to stamp out copies of a function that all have the same behavior, right? And in the previous slide, I have these 2 functions. One adds 1 to ints, one adds 1 to doubles. If I want one to add 1 to complex numbers or long double or whatever, I would just keep adding overloads and overloads and overloads. But we have the function template, which allows us to stamp out copies for any type that we want. And again, those are instantiated on demand. They get name mangled slightly differently yet again. Notice that the template +1 instantiated with int is a different entity indicated by a different name mangling than in the previous slide, the +1 overload that took an int. Things about template. I'm going to go a little bit into templates, and then we're going to drop templates for a bit, and then we're going to come back to them later. Let's go a little deeper into templates. So when I call +1 of 42, where 42 is an int, the compiler can use type deduction to know that, okay, you want the +1 that takes an int. And, well, 1 doesn't really seem to exist yet, so I'm going to stamp 1 out for you, instantiating this template. When we call +1 of 3.14, well, that's a double, so you must want a +1 that takes a double. I'll stamp 1 out for you. I'll instantiate it. We can also tell the compiler explicitly, even though I'm passing 42, which looks like an int, I do really want the version that takes it as a double, and like, please convert 42 to a double. I can explicitly say I want +1 of double in angle brackets, providing the t explicitly. And vice versa, there are a couple contexts which are not function calls, where the compiler will do type deduction for us, which is actually really handy. For example, I can take +1 here, just the name +1, without saying +1 of int or +1 of double. And as long as I'm storing it into, let's say, a function pointer that takes an int and returns an int, the compiler can say, oh, well, you must want +1 of int. It is smart enough to do that. You might say, well, what if I took this +1 and assigned it into like auto? Then how does it deduce what the type of t is, and then how does it deduce which +1 to use? And the answer is it doesn't. A function template is not the same thing as a function, right? The function template is a source level sort of construct, and if you use it in a context where it's ambiguous, the compiler will give you a diagnostic of some sort. In this case, client complains about incompatible initializer of type, and then just in brackets it just says overloaded function type, because the type doesn't have a name, it's a template. All right, one more little thing. The first puzzle. There are 3 puzzles in this talk. One more thing about templates before we move on. Here I have a template, a function template named kitten. It has a static local variable of type int, initialized to 0, and every time we call kitten, we're going to ++ that variable, right? I call kitten of 1, where t gets instantiated as int, and that's going to print 2. Yeah, okay. And then I call kitten again with 3.14. This is even harder math, I know, but it's going to print 4.14, yes, not 5.14.
Even though the int was static, because it's a different static int.
Yes, even though the int was static, because it is a different static int. Here's the code gen. We have 2 instantiations here with different name manglings and different code. You notice that the one for int, it's involving lots of sort of inty operations. And here's the one for double, and it does some stuff with the XMM registers, with the double registers. So they have different code gen, and going along with that, each of them gets its own set of static local variables and so on. Here we have, this is the x for the double version, and this is the x for the int version. They don't share memory. They're 2 completely separate variables because we have 2 completely separate instantiations of this template. This is made a little bit clearer, like you might say, well, that just seems dumb. Like, why did the standards committee make that decision? Why don't we have 1 variable x? That's what I want, right? Well, not really. Because what if instead of int right here, we made it type t? We made it something template dependent. You can do that, right? You can have a local variable of template dependent type. For example, in this case, when I have a kitten of int, t is int, and x is of type int. When I have a kitten of double, well, my my x now for this function needs to be of type double. So it's kind of obvious at this point that, well, we're going to need 2 different variables, and the int variable for the int version, the double variable for the double version. So, templates and statics. Little sneaky there. All right, we'll come back to templates later. Let's go back to what other crazy things can we do with functions in C++. Oh, you can make member functions. I can have a class. I'm going to call this class plus. It's going to have a member variable named value. You can instantiate it or get an instance of this class by calling its constructor. And it's going to have a member function, which I'm just going to call plus me. If I have a plus object, I can call like my plus object dot plus me, give it an int, and it gives me back the sum of the int I gave it and the int that was given in its constructor. Another little digression. I love digressions. When I call plus dot plus me of, let's say, 42, how does the plus object know to go call this code? Is there some, this object has to know, oh yeah, when you call plus me on me, that means this code here. Is there some sort of pointer to that code somewhere? No. C++ is not Java, thank God. The Java approach, there would be, right? There, every object is allocated on the heap and has a v pointer that points to a table of here are all the behaviors for this object. That's nice in that we can now pass a pointer to this object around, and the object knows its own behaviors. It is not so nice in that, well, now we've got like 1, 2, 3 pointers here that you have to follow whenever you want to do something with this object. C++ lets you do this via virtual member functions, which we're actually not going to talk about, surprisingly. But of course in C++, it just looks like this, right? On the stack, we have our plus object just sitting right there. It doesn't need to be on the heap. We don't want to use the heap. We don't want to use dynamic memory management. And the function, the implementation of the function is just sitting there in the static code, and there is no linkage at all. There's just sort of a implicit, like, you just know, the compiler just knows that when I'm doing something on a plus object, of course I'm going to use plus's member function. Okay, so yeah, C++ lets us get rid of all this dynamic memory management and whatnot that you have in Java and so on, but you knew that because you're here. All right, so class member functions. Now, this member function, I just named it plus me. But let's say this was the only thing that I could do with a plus object. C++ also gives us the ability to do operator overloading. So I could actually overload the function call operator on my plus object, right? Exact same code gen as before. The only difference is the name mangling has changed a little bit. This name mangling right here has changed from being the name of the class and the member function to just CL, which stands for call. So let's see. So I can overload an operator. And then when I call it, you notice the call changed from plus dot plus me of 42. Now I can just say plus in a pair of parentheses, and the compiler will know, oh, okay, you mean to call the call operator here. And of course, it puts the call operator in there statically because static typing. Now we can do something kind of nifty, right? We take this code I just wrote, where we have this class and the call operator and the constructor, and we create objects of this type using the constructor. And the syntax highlighting that I've used here is in red, in bold, I've put the irreducible complexity. The stuff that, well, this is just what it does, right? I can't get around the fact that there is a member named value and that my operator paren takes another int, and that what it does is add them together, right? That's the semantics of my class. But everything in the light green there is just boilerplate. I don't want to have to write that. That's a lot of boilerplate. So let's just get rid of all the green. Okay, all the green is now gone, except for a lot of brackets. Actually, one of each kind of bracket. It's a very fair language. And a little equal sign there. So now we're saying very succinctly what we want to say about this entity in our code. We've thrown away all of that reducible complexity about what is the name of the class and the fact that you have to write out its constructor. And now we're just saying it's got a member named value. Here's the initial value for that value, by the way. We're going to pass in 1, but we could pass in any expression that we wanted, of course. And it has an argument, and we have to give the argument's type, and we have to give the argument a name because we're going to refer to it later, right? So we give it a name x, and then we say, here's the behavior, and that's it. And we wrap that all up, and that is a lambda expression. And we use it exactly the same way. You notice that the assert down at the bottom that's checking the behavior of our object plus, where before it was constructed explicitly as a plus object. Now it's just constructed as a lambda expression, which produces one of these anonymous class objects, and it behaves exactly the same way. And the code gen is exactly the same implementation. except that now, of course, we don't have a capital P plus object anymore, because we just removed that name from our code. There's no more names in our code. So the compiler makes up a name for this class, and at least in Clang's mangling scheme, it just says $_0. $_integer is the naming scheme for these anonymous objects. Let's see. So now on the stack, instead of having plus a plus object, I have plus a $0 object. And instead of calling the plus call operator, it's calling the $0 call operator, indicated by the mangling down there in the fine print that I don't know if you can read in the back. And the code gen is exactly the same. Awesome. Oh, by the way, I do want to point out that this value equals 1, this is C++ 14 generalized lambda capture, also known as init capture. I like it for reasons you're about to see, but be aware that if you're in C++ 11, you don't actually have this syntax. You just assumed you didn't know everything about lambda as well. Haha, you don't. Anymore, so. Yes. For almost 2 years now, you don't know everything about lambdas. Before that, you did, though. And so this gives us the ability to have sort of Lisp-style, functional programming style closures without heap allocation and without garbage collection. Because you saw we just built that out of the building blocks that already exist in C++, right? And we can all write code that uses classes and so on with the allocating them on the stack, RAII. We know how to write that kind of code without invoking the heap and garbage collection and dynamic typing and so on and so forth. So since I can then take that code that we had and remove all the boilerplate and get a lambda, obviously we can also implement lambdas without garbage collection and dynamic typing and so on and so forth. So those two things do not go hand in hand as you might think if you looked at C++ 03 versus like Scheme and said, oh, I wish I had lambdas, but I can't get them without this other baggage. Well, yes, you can. Here's an example of how to use them. Let's say that I want to std sort this vector of objects by some property. I can make myself up a little closure object here as a lambda expression. I'm going to take this prop that was passed in by the user, and yeah, I'm passing things around by value. Yeah, that's probably okay, move semantics, right? I'm going to capture that property. I'm going to make a copy of it inside my closure. And now that I've captured that thing, which I'm naming P here for convenience, it's prop outside, but it's P inside, just to make sure we know what we're talking about. Inside I can say, I'm given two objects, and I compare that field of them. And then I can take this pless object, and I can pass it to std sort, and std sort will sort things based on this predicate. Does that all make sense? I think we're about to see an example of that. We are, okay. So here's what we might have coming into the function. I have this, I have my prop, which is a std string, and so it controls some, hello world out there on the heap, which is the name of the key I'm sorting by, so maybe hello wasn't the best example. And then I make my closure object, so that's going to be a $sign something, $1 object. And it is going to have inside it, captured, it's going to have a member variable, which I've named P. That's that P right there. And it's going to be initialized to a copy of prop, so it's going to copy out the hello right there. And that's what it's going to look like. So again, the lambda itself is not living out on the heap anywhere. There's the heap involved in this case because we're controlling std strings. And again, there's this sort of magical compiler static typing linkage between these things that is not represented in the runtime, at runtime. Okay, so let's see some other alternative syntaxes for this. So I said this was the C++ 14 generalized capture. In C++ 11, you have a more restrictive version. You can't give things different names, but you can say, I want to capture the local variable in my outer scope named prop. I will capture it with that same name, prop inside. But notice that prop inside refers to that pink prop that I captured, not to the prop in the outer scope. So you can write that in C++11. Also C++11, and of course also in 14 you can continue to do that, but I don't really think you should. I don't know, I like explicit names. So we can also just say, I'm going to capture everything I use inside that you don't know what it is, go look for it outside and make a copy of it, please. So you can give a default capture semantics. This many people consider to be a bad idea in general. It's certainly good it's in the language. There are things you can do with it. You can put it inside macros and so on. That makes it very nice to have in the language, but probably not something you should do a lot. Okay. And then, and the other thing going on here, by the way, we were talking about doing all of this without garbage collection. You can see that once I've made this copy, I can then have the original prop can even go away, and I just pass my lambda around. And it's like there's no dangling references or even reference counting going on. It's just, well, I made a copy. Now it's mine. So I can get rid of the original if I want. But what if I want to capture a reference? Because this prop that I'm making the copy of, this is a really big box. I'm making this big copy. I don't want something this heavyweight. I want a nice lightweight pointer. So I want to be able to capture a reference. So what do I put in my capture list here if I want to capture a reference? Well, I could do that. Yes. You could do this, but you shouldn't do this. What you really, the built-in syntax for it is put an ampersand in front of the name of the thing you're capturing, and that magically the compiler, it's not magic, but it's a special case where the compiler will say, oh, okay, now you want a reference to it. Okay, I'll give you a reference.
So hopefully it's a simplifying question. What's the difference between that? I don't know. What is the standard ref type that you used in the previous slide?
What is stdref? Stdref is a function that gives you back a std, I think, reference wrapper.
So is that syntax in C++14 therefore using auto so that it knows that it's a reference type? I thought auto drops reference type, so
a reference wrapper is a...
it's a wrapper?
Yes, it is not an actual reference. It's not an actual T ampersand. A reference wrapper of T is an actual value type that you can copy and assign and whatnot, but it behaves like a reference. So that when you use it, it basically just has an implicit conversion to T ref, I think.
There's an implied auto in front of the P equals.
There is an implied auto in front of the P equals. Yes, basically yes. However, if you think of it that way, then you'll start thinking, oh, well, I should be able to put double ampersand P equals prop, and that should capture an R value reference. No, that doesn't work. I should be able to put star P equals prop, and that should capture an auto pointer. No, that doesn't work. It's a very special syntax that means if you don't put anything, it captures by value. If you do put a single ampersand, it captures by reference, and that's it. Those are the two kinds of things. And similarly, if you... we saw that you can capture everything by value by putting the equal sign. You can also capture everything by reference by putting just the ampersand. And that means anything that I use in my inner scope that I haven't defined in my inner scope, go look for it in the outer scope, and if you find it there, capture it by reference. And I also skipped over the slide where in C++11 you can capture named local variables with the same name inside by reference as well. All right. But beware of dangling references. Right, if you capture everything by reference, and then you get rid of the referred to stuff, then you have dangling references, dangling pointers, which we all know from this morning's keynote are terrible. So be very careful when you do this. Yeah, that problem is solved. Yes. So don't worry about it. Basically, capturing everything by reference is really, really great and convenient for lambdas that you know are only going to go sort of down your call chain and never escape upward into your caller, right? Then capturing everything by reference is just the simplest thing to do. And if you're not doing that, you probably shouldn't be using a default capture mode at all. You should just spell out exactly, I want to capture this and this and this. By the way, if you literally capture this by, let's say, copy, what are we capturing? Capturing a pointer by copy, yeah. So it will look as if you're capturing it by reference, basically. And it will do this even if you are referring to, if you're not writing this in your code, but you just say, I want to capture everything by copy, and then I refer to a member variable, my member, whatever. It will say, oh, well, how do I get my member? Well, that's really this arrow my member, so I'll capture this by copy. And you'll think you're getting a copy of my member when in fact you're not. You're getting a copy of this pointer. I wish I had a slide on that. Okay, so just to sum up default capture modes, here I have a couple of factories called increment by. You pass in one integer. This is basically a factory for our plus lambda, right? You pass in the number you want to add to things. So for example, I can call increment by of 5. That gives me back a lambda, which I'm naming plus 5. And then if I call plus 5 on 2, I get 7. The good increment by captures the y by copy, and it all works great. Bad increment by captures that y by reference, so that the lambda that I'm returning back out of my scope has a reference to a local parameter, local variable. Returning a reference to a local variable obviously doesn't work. All right, a couple other grab bag features of lambdas. They are convertible to raw function pointers as long as you don't capture anything. That's super useful. If you do capture something, then of course you can't, because you can't turn like an arbitrary, going back to our original capital P plus object, I can't turn a capital P plus object into a function pointer, because where do I put the data? But if I don't have any captures, then my plus object is basically just a handle to its operator paren, which takes a this pointer, but it doesn't do anything with it because the this doesn't control any data. So really, it's just a pure behavior. It's just a pure function. So in that case, the language actually allows us to convert it to a function pointer. Variables with global scope are not captured. There's a puzzle about this later. This is the spoiler. And lambdas may have local state, but not in the way you think. Here's a puzzle. All right, puzzle number 2. What have we got here? We got a global variable g, which I initialized to 10. And then inside main, I'm going to set g to 20. And then I'm going to call my 2 lambdas here, which in the traditional style I'm naming after cats. We have kitten. It captures everything by value. And we have cat, which captures only g by value. What do we think this is going to print? I heard 11 and 11. I heard 1 and 11. I heard 21 and 11. I also heard 21 and 21. Okay, I think, is that all the... Okay, I think we've completed the square.
Access violation.
21 and 11. And here I've color-coded what's going on. So if you can read my mind with the color coding. So the global G, which is purple here, globals are not captured, right? Because why would you need to capture a global? It's global. Everyone can see it.
Because you told it to, but go on.
Because you told it to. Well, no, I just told it by default. If there's something in my scope that you don't see outside, just assume that it's in the outer scope. But G, of course I know what G is. G is the global variable G. So kitten doesn't need to capture anything. It uses G, but doesn't need to capture it. It's global. It knows its address. Its address is never going to change. So kitten is actually going to basically track updates to our G as we make them. So that's why it gives us 21. By the time it actually tries to use G, G has already changed to 20. Cat, on the other hand, we explicitly told it, I want you to have a local, a non-static data member in this $1 class. I want it to have a non-static data member whose name is G, and I want its initial value to be the result of the expression G. The result of the expression G is 10 right now when I create cat. So it gets a local G controlled by the cat object with value 10, and 10 plus 1 is 11.
So this is the same in C++ 11 again, where you would just have G. I mean, I know you really like the G plus G thing, but it would work the same in 11, where you just say that. Oh, that next slide.
Yep. C++ 11 either doesn't have this problem or has it worse, depending on which compiler you use. In C++ 11, if I use the format where I don't have the equal sign, I just say, please capture G, that is a constraint violation and should be diagnosed. As of this writing, Clang diagnoses it with an error. GCC diagnoses it with a warning and keeps going. And I do not remember what it does. So be aware that even if you name the global, if you use C++ 11 style, A, that is a constraint violation and requires a diagnostic, and B, you may not get a diagnostic.
Same thing if you capture by reference.
Same thing if you capture by reference. Well, in that case, like, it definitely wouldn't matter, right? I mean, if you're capturing it by reference, you know you're not getting a copy. So, yes, it would still be a constraint violation, but I can't imagine anyone thinking that they were going to get any behavior different from what they got. So, all right, time to revisit statics. Here I have a kitten factory. You pass it in a value that you would like to add. The actual behavior of this lambda is going to add up a bunch of stuff, right? Two of the things it's going to add up are the value you pass to the factory, C, and the value you pass to the constructed lambda, D. Also to that, we're going to add the values of two statics, which we're going to be plus-plussing every time you call the lambda. One that's static in the factory and one that's static inside the lambda itself. And now we're going to make two kittens, one with value 1, one with value 2, and we're going to call them, we're going to call the first one twice, and we're going to call the second one twice, and the question is, what does this print? And I don't even want to think about this, but if someone out there does, just shout out the answer and I'll tell you if you're right. Here's the answer. All right. So what's actually happening here? Well, we're making a kitten of 1. So we're going to come in here, and the A inside make kitten is going to start with value 0. And it's going to return a new closure constructed from this lambda expression. So it's going to be an instance of a $0 class for some value of 0. And the call operator of this class is going to have the following behavior. It's going to have a copy of C, because we're copying everything by copy, capturing everything by copy. We're going to increment the A, which is just global, like there's one of it inside make kitten, right? We're going to increment the B, which is static local inside this scope. And then we're going to add the C and the D to it. This is already confusing me. Too many variables going on here. Also post increment. Why did I choose post increment? But the gist of this is that, of course, there's only one static A, right? Because it is in the scope of make kitten, and there's only one make kitten. But how many B's are there? Do we have one B or two B's? The answer is we have one B, because B is static in the scope of this anonymous class's operator pren function. Right? It has a static local. So it's gonna look kind of like this. Oh, and this doesn't show up the same way as it showed up before, but just pretend this is all in one line. So we have a single static A, and we have a single static B, whose name mangling indicates that it's the B that belongs to the call operator of $0. I wish I could just, get rid of that to make that name mangled thing clearer. We have our kittens, K1 and K2. They each captured a C, and they're statically, through the magic of static typing, they use this code, which refers to the A inside makeKitten and the B inside the call operator. But there's only one B, and that's why they see each other's updates to B. Because there is only one call operator. Yes. The $0 class has a single call operator, which has a static local B that it refers to, but only one of them. So statics inside member functions, behave the way that you might already know they behave.
Well, I mean, is it appropriate in this case to resolve the conundrum by saying this is created at compile time? It's not going to create a different stamp, as you called it, just because you called it again a little bit later.
Right.
So it's the same one because it was stamped once at compile time. And those calls are static calls. They're not dynamically figured out through some V table like we were talking about previously. So there's just one of those methods that's just being returned in different ways.
Yes, I would go with that. But I want to say that it's not super obvious that that's what should happen, right? Because this lambda expression here does have this, like we say very explicitly, I want there to be a static int named B inside this scope, and the committee could have decided, okay, let's make it so that when you declare a static locally inside this lambda thing, that really means that we get one per closure. Like each one gets their own, and it's initialized to 0. Why didn't they do that, you might ask? Because we already have a way to do that. So here's the situation we have now, right, where each of them gets their own C because they captured it, but they share a reference to B because there's only one B. And then if one of them modifies B, the other one sees the update. And that's not what we really wanted in this case. Let's suppose that's not what we wanted in this case. What we wanted, what we thought we were getting, and it turned out we weren't, is that we thought we were getting a B in each of these closure objects. So how do we actually achieve that? What is the syntax provided for that? Well, it should be pretty obvious that what we're doing with B here, putting one in each closure object, is exactly the same thing that we had done with C. Right? So we should be able to use the same syntax that we used to get this C to also get a B. All right, so all we need to do is just capture something, and we'll name it B, because why not? We'll initialize it to 0. And because we're going to modify it, we'll have to add the mutable keyword to make sure our lambda can modify its captures. But there you go. If you want some extra state per closure object, you just stick it in the capture list, because the capture list is where your member variables of this anonymous class go.
Could you also declare it inside the braces, but without the static keyword?
Could you also have declared it inside the braces without the static keyword? Yes, but then it would be a stack variable. It wouldn't hold its state.
Well, it's kind of in the stack there anyway. I mean, it's in the stack space. Well, they're different. I don't know. Okay.
This B is not on the stack. Okay. I said stack, but
They're inside other things.
They're inside other things that can then be copied and put somewhere else, or passed return values, or passed up or down.
You can't do that with C++11 syntax, right?
I think you can.
But you can't do this with C++11 syntax as written. What you would have to do is create a local variable named B, initialize that to 0, and capture it by name. Yes, it's ugly, but that's why I love the generalized capture syntax.
Sorry, this is probably the most basic one, but could be a theoretically be any type, and could you call a constructor there versus, just calling some b int 0, just call it some class type b and have it call its constructor and then pass that down?
Yeah, could b be something other than an int? Sure, yeah. It could be a std string. It could be a arbitrarily complicated class.
Specifically declare the type of b if it's not say an int, or do you just put equals and then whatever it's going to be?
Do you need to say the type of b? No, in fact, you can't. The only thing you could do there is say b equals and then spell out the type. Like I'd say b equals int of 0 or b equals std string of hello world. This is similar to, I know Herb Sutter has this idea of almost always auto, which is catching on to a certain degree. And this is one place where it is always auto. You don't get a choice. There's no way to specify the type on the left-hand side of the equal sign. If you want a specific type, you must either write an expression that gives you that type or write an expression that gives you that type by means of a cast. Okay, so there we go. Per-lambda mutable state. So I just snuck this mutable keyword in here. If we're going to plus b, we need to say mutable. What is that actually doing? Notice that mutable is not going on b itself, and there's no way to do that. It's going on in the same position that you would expect to find the const qualifier in a member function. Right? I say operator pren const, and then in a lambda I say something pren mutable. The reason for this is that lambdas, by default, their operator pren is always const. It was decided that, generally speaking, you don't want to modify your captures. If you are modifying your captures, that's probably a bug. You would really like us to warn about that. So your operator pren on their anonymous class $0, whatever, is always const unless you say mutable, and that makes it non-const. So everything is shifted one level down constward from what you would expect. So saying mutable gives you an operator pren on this anonymous class object, which is not const, and therefore can modify the captured member variables.
How come A wasn't captured by copy?
How come A wasn't captured by copy?
Outside static.
Right, and we said capture everything by copy if you can't already see it. Right, we had to capture C by copy because there's no C in the scope. But there is, again, only one A. Globals and statics in general are not captured by copy because we already know their address. When you say A, we know you're talking about this A. We know we don't need a copy of it. It's right here. Its name is A. And so that's why it wasn't captured. All right. So generic lambdas from scratch. That was the whole point of the talk, right? Okay. Let's go back to the beginning. Class member functions. Class member function templates. Let's go back to our plus with a plus me member function. Let's now make that a template. Now instead of taking int x, we're going to take tx for any type t, and we're going to return a t. Really, I guess we should be returning auto and just let type deduction sort of figure out what the type is. But t plus int gives you t, right? Okay, so now we have a template, and we can instantiate this template. We can say, once I have a plus object, like plus of 1, I can say plus.plusme of 42. That will instantiate plusme with int, and we'll get something that name mangles to something like this, and does integer operations. I can say plusme of 3.14. Type deduction will say, aha, t wants to be double here. I'll stamp out an instantiation of plusme for double, and I'll get some double code gen. Okay, looks great, right? Good. Okay. Okay, what did we do the next thing? Call operator. Boom. All right. Replace plusme with operator pren. Now the name mangling has changed a little bit. We have CL there, where before we had plus me. The way we call it has changed a little bit. Okay. Now we make something kind of nifty. Here's the reducible complexity and the irreducible complexity. Irreducible in red, the reducible complexity in green. We're going to say make me a plus where the value is 1, and then assert that, I can do this, the same thing I did before. Let's take all that boilerplate in the green, and let's get rid of it. It all goes away. And now I have the same thing I had before. Before I had an instance of the plus class where its operator paren was a template. Now I have an instance of an anonymous class where its operator paren is a template.
This is 14.
This is C++ 14 at this point, yes. If you wanted in C++ 11, you write this. And I learned at lunch today that there are places in Boost that really expect something that behaves like this. And so 14 is great because now you can pass them nice simple things instead of having to write your own templates. So here we go. All the same stuff as before. You say I want every instance of this closure object to have a value. I will initialize it to, in this case, 1. And I have an operator paren that has 1 argument. I call it x. But what is its type? Its type is auto, which is the new magic catch-all keyword that we use every time we don't know what other keyword to use. It's replaced static in that respect. So you say auto x, and that means this is a template, figure it out. You could say auto star x or auto ampersand x, and that would mean this is a t star, this is a t ampersand, figure it out. But in general, we would write like auto, or we would write auto ref, which would turn into a t ref, which is a universal reference or a forwarding reference. So for perfect forwarding. All right, so generic lambdas. All right. Here we have another puzzle. I have a kitten. It's a generic lambda. So it takes auto t. And it has a static local named x, initialized to 0, and I return plus x plus the value you give it. So kitten of 1 is 2. Kitten of 3.14 is 4.14, right. For exactly the same reason as in puzzle number 1. Did I forget to change that slide? I did. Puzzle number 1, Redux. Right, so now we're circling back to templates, if you didn't notice already. So yeah, we have one entity here. Its name is kitten. It is no longer a template itself. It's not an overload set. Kitten is a real thing of type $0. It's an object. I can pass it around. We know its type. But because its operator paren is a template, whenever we're using operator paren, we're actually instantiating that template. And every instantiation gets its own set of function local statics, for example. So that's why we get this behavior again.
You're going to answer, I bet. But can you specify then on the lambda call which one you want without just doing like a cast on the parameter? Does it have angle bracket syntax on it?
Can I use angle bracket syntax to say kitten of int or kitten of double? I believe not, but I am not sure. I don't actually know. And if you can't, it might be coming. I'm not sure. Seems reasonable-ish, but probably not. Because remember, kitten itself is not a template. Mm-hmm. Right? So kitten of int is definitely not a thing.
Maybe you could cast it to a function pointer first if you really care.
Right. I mean, I believe that I could say, like, I'm going to get the address of, like, kitten.operator paren of int. Like, there's probably some syntax to make that work, but it's completely ugly, I'm sure. So in general, no.
Could that auto of t be actually like a vector of auto of t? Can auto be used anywhere like a template t?
Can auto be used anywhere? No. Like, can you have like a vector of auto? No. You can say vector of t and have it deduce the t for you. And you can say sort of similar things like auto star and auto ref, but I don't think you can say vector of auto. And I know there's been a proposal for 17 to let you say that, but I don't know what happened to it or where it is. Vector of declarativity? What? All right, so generic lambdas. Generic lambdas behave in this confusing way just like templates because they are templates. They're templates under the hood. All right, we have 10 minutes left. I think we can get through all of the slides and maybe not the bonus material, but hey, that's why we have lightning talks, right? Let's do Variadic function templates just to prove we can. Variadic templates, right? Yeah? Okay. We have a class plus. It has an int value. It has a constructor. It has an operator paren, which is a template which takes an arbitrary number of parameters of types p, where p represents a parameter pack of types. And it's going to return the sum of all of those and also the value. Let's see. Right, so I can say plus of 42, 3.14, 1. And that should give me 42, 43, 46, 47.14. Or I could say plus of foobar and 2, and that should give me bar, right. Because char stars. All right. All right, so we take the code that we wrote before. We have the reducible complexity in green. We have the irreducible complexity in red. We replace all the green with one pair of brackets each. And you'll notice that we took the P, which was a parameter pack, capital P, I mean, that disappeared. Instead, we just say auto, and that means I am a template, figure it out. And auto ... is a parameter pack of, I don't know, figure it out. So here I have a generic variadic lambda, which takes any number of parameters, and it's going to take them by value or by copy, because I said auto ... and not auto ref ... and it's going to add them all up. Also in C++ 11 syntax, I can capture a parameter pack. So we talked about, so this is going to be confusing because I'm doing them right after each other, but here's how I make a variadic template lambda, where the argument list is a parameter pack. But flip side of that, I might want the parameter pack in the other set of brackets, right? I might actually want a non-variadic lambda that captures a whole parameter pack that was passed to the caller, or to the creator of this lambda. I might actually want both. That's also fine. But in this example, this is going back to our sort by properties. So I have a vector of objects, and I want to sort them now not just by one property, but by a bunch of properties. Possibly empty, actually, but we're going to pretend that the empty case doesn't exist. And I'm just going to pass in a whole bunch of strings. I'm going to say sort by key 1, key 2, key 3. So there, my type names captured by P are going to be like std string, std string, std string. Props is a parameter pack representing those 3 strings. And I can capture that whole pack by copy in my pless. And then I can expand it back out again when I need it inside the lambda. And look at that, lexicographic sorting in like 1 line of code. So that's nice. Now you might say, well, we're going to get to that in a moment. Slight digression, capturing by move. Here is our original example where I'm capturing the string by copy, but copies do take a lot of memory, so maybe I just want to do a std move. I can do that in generalized capture, init capture syntax in C++ 14. Can I capture a whole parameter pack by move? Can I say this? Big old nope. Can you do forward? Big old nope. And there are good technical reasons for this. If you Google it, there's a Google Groups post by, I think, Richard Smith, someone who knows, that explains that, well, this is really tricky because you can't have a non-static data member that is a parameter pack. That doesn't make sense. So you can't do this yet, but maybe it's coming someday. I wish, because that would be nice. What you can do instead is make a tuple out of your whole parameter pack, move things into the tuple, and then std move the tuple into your lambda, and then in your lambda you can unpack it, which I didn't even write because I don't think that that's possible in more than about 10 lines of code in a helper function. So can't do that. And I don't think we're going to talk about std bind, so you might as well ask your questions. In the back? Can't you do that with apply from the experimental extensions TS? If I were only calling a function on the parameter pack, yes. But you'll notice that I wasn't just calling a function on it. I was taking the parameter pack and doing a sub p for every p in the parameter pack, and b sub p for everything in the parameter pack. So I could use apply actually with this. All I need to do is call the std square bracket functor, like std less and std plus. There's one of those for every operator. So all I need to do is call std index, which doesn't exist. They just got around to adding unary not in like C++ 14. Eventually they will work their way through all of the operators, but they haven't gotten to square brackets yet.
Basic question, going way back, but I didn't want to interrupt the flow. When you do something like a square brackets p, where p is what they're capturing from props, what is that evaluating to? I mean, in the earlier example, it was the string hello. How do you know what a bracket hello would be?
How do I know what a bracket hello would be?
So it's some address of an object a, and you're taking the address of that and hello?
Oh, well, a here is a reference to object, which is a std map. So it's using the map index operator to say, give me the value associated with the key hello.
Oh, I see. Okay.
And I heard someone ask, what is tie? Tie is like make tuple, but it takes references instead of making copies. So what tie is doing here, std tie, but there wasn't room on the slide to write it, is basically expanding a sub x for all x in props. So that gives us a sub hello, comma, a sub world, comma, a sub for all of the p's that you passed in. Taking references to all of those, wrapping them up in a tuple. On the other side, we do the same thing for the b's, and then we use tuples less than operator to do a lexicographic comparison of those two things. And I think we're probably out of time. Well, all right, one more. What's that? Experimental apply takes a function and a tuple and calls that function on the elements of the tuple altogether. So it takes the tuple that's captured the parameter pack and allows you to use it as the parameter pack to a function again. Sort of the inverse of make tuple. All right, thank you.